I'm going to describe a zero-knowledge proof system called BooLigero. BooLigero yields a concretely smaller proof size than the original Ligero system for Boolean circuits. I'm Sarah Scheffler. I'm a PhD student in cryptography at Boston University. This is joint work with Yaron Gvili and Mayank Varia. So we start with a common example use case of zero-knowledge proofs on the blockchain. Suppose I have a financial contract, I've posted the hash of the contract, and I also want to verify that all of the inputs to the contract are between 0 and 255. I want to prove all of these things in a post-quantum way, with no trusted setup, while preserving the privacy of each input and output. So we can do this using a zero-knowledge proof. When it comes to zero-knowledge proofs, there's a whole garden of different systems out there, and you generally want to pick one suited to your use case. On the one hand, we have proofs that are fast, but large. These are typically based on some flavor of multi-party computation, like ZK-GC or MPC in the head. On the other end of the spectrum, we have proofs that are very short or succinct, proofs like snarks. These tend to take a much larger time to compute, or they rely on trusted setup, or they use some assumptions that are inherently unfalsifiable. So if you want to, for example, put your proofs on the blockchain, you probably want them to be fairly small. So you probably don't want the large MPC-based proofs, but you also probably want to avoid costly ceremonies or trusting a centralized setup process. So there's interest in this middle area, proofs that are medium size, but require no trusted setup. Furthermore, you might want to zoom in further to proofs that maintain their security properties, even in a world with quantum computing. And there are really only a handful of protocols that meet all of these requirements. The main systems in this area are Stark, Aurora, Ligero, and lattice-based zero-knowledge proofs. None of these is strictly better than the others. The choice involves a trade-off between proof size, proof of runtime, and round complexity. And we choose to focus on Ligero for a few reasons. First, the lattice-based zero-knowledge proofs of Baum et al. In 2018, the concrete performance of these proofs still remains unknown, so we don't focus on them. Stark has an asymptotically smaller proof size than Ligero, but is concretely larger for small to medium circuits, and it has a larger prover runtime both asymptotically and concretely. And Aurora is smaller than Ligero, but it has a concretely higher prover runtime and an asymptotically higher round complexity. In this work, we take Ligero as our starting point, and we add some improvements that concretely reduce the proof size. We do this in two ways. First, in the original Ligero system, if you wanted to compute a Boolean circuit, representing each bit required using an entire larger field element. How large? It depends on the circuit, but there's a minimum size required to make the system work at all. So in practice, the field size tends to be about 14 to 18 bits. So since we can fit many bits into a single element, we can expect to improve the size by about the square root of that number, so by about 4 times in the best case. Second, we also add additional constraint tests that work differently than the original Ligero tests. Many of these are highly batchable and can test many constraints for only a constant overhead among many variables. So these additional constraint tests we use for both doing standard operations like bitwise and also for other types of constraints like public bit masking or rearranging bits within or between words or some other things I'll get to later. Concretely, we get about a 1.6x improvement over SHA-2 for many SHA-2 computations compared to Ligero, and we get a 2.8x improvement for many SHA-3 computations compared to Ligero. So in this talk, I'll give first a brief review of Ligero, and then I'll describe each of these improvements. So Ligero is a system that proves constraints among variables. If you're trying to compute a circuit, the first thing you do is take all the wire values and arrange them in a matrix. And you'll notice that the number of rows and the number of columns are both O of the square root of the circuit size C. So if your C has, this many wires, the number of columns and the number of rows are both square root of that number. So Ligero is going to verify constraints between the circuit values provided. So for example, it can show a linear relationship between several variables, or it can show that two variables multiply to a third variable. If we're evaluating an arithmetic circuit, we convert each gate into one of these constraints. So addition gates become linear constraints, for example, x plus y equals z, and multiplication gates become quadratic constraints, so x times y equals z. So now the circuit is represented as constraints among the variables in this matrix. And then we encode the matrix. We take each row, and remember each row contains many wire values. We take each row to be the message for a Reed-Solomon encoding scheme, and we get a randomized code word that decodes to the message. So in the encoded Ligero matrix on the right, each row is a Reed-Solomon code word that decodes into one row of wire values. Note also that for this encoding scheme, the code words have the same asymptotic complexity as the number of columns in the original matrix. So the encoded matrix is also O of root C by O of root C. And this is how Ligero achieves a sublinear proof size. The proof is essentially going to be a subset of the columns and a linear combination of the rows. So the proof size itself is also O of root C. So BooLigero provides two main improvements over original Ligero. Both of these improvements act on the unencoded Ligero matrix, and then the process of encoding and checking constraints largely works the same way as it did in the original system. So what are these improvements? First, for Boolean circuits, we're going to pack more bits into a single element, which will save us a square root factor of log of the smallest field size that Ligero could use for that circuit. And then second, and much more involved, we're going to add new constraint tests that work in a different way. These will reveal some of the unencoded Ligero matrix directly by adding another two-way round to the protocol. And this will allow checking additional constraints beyond just linear and quadratic constraints that were fixed ahead of time. So I'll start with the first improvement. In plain Ligero, when proving something about a Boolean circuit, the standard proposal is to use one field element to represent one bit. So each of these field elements represents a single bit, and a quadratic constraint is added to each of these elements to prove that it is either 1 or 0. So you add, x squared minus x equals 0 for all of these elements. This works, but it involves a lot of wasted space. So we're potentially using a 14 to 18-bit object to represent a single bit. So the first BooLigero improvement is simply to pack the bits, thus shrinking both the unencoded and encoded Ligero matrices by this factor of square root of the bits of the field. So we're switching here from a prime field to a GF2 to the W field. And we can now think of our elements as W words of bits. This comes with some caveats, so we don't get to do this for free. So first, what if we did want to manipulate individual bits? Well, it depends on the circuit that you're trying to do, but there might still be times when you need to create a whole separate variable to represent one of the bits. Although we do provide many methods in the later part of this talk to find some creative ways to avoid having to do that in some cases. But more importantly, the fact that we are now in GF2 to the W instead of GFP changes the operations. So in GF2 to the W, addition becomes bitwise XOR, and multiplication in GF2 to the W is not what most people think of when they're thinking of multiplication. And the original Ligero tests, if we just use the same tests written by Ligero, now test these two constraints rather than anything else. So this is BooLigero, so we want to be able to test Boolean circuits, which means we want to be able to test at least XOR and AND. We can easily get XOR from Ligero's test, but we also want to be able to express and maybe some other things as well. So fortunately, we are able to use the existing Ligero tests, plus the extra framework I'm going to describe shortly, to build tests for a much wider range of functionalities. So one of these is bitwise and and which is great because now we can do standard Boolean circuits with XORs and ANDs. We can also re-implement arithmetic addition, albeit in a more complicated way than in original Ligero. We can do range tests, that is showing that variables are within a certain range. In this talk, I'll describe how to do this for a range that is a power of 2. We can also do this for non-powers of 2 with a little bit more work. And then we have several other operations like masking, zero testing, arbitrary sets of bits, and rearranging the bits between variables or within a variable. So by switching from a prime field to this 2 to the W field, we can definitely do our Boolean circuits, because we have XOR and we also have several other tests at our disposal. And using these tests might actually allow us to reduce the size of whatever circuit we're trying to test, because we can potentially replace a complicated subcircuit with a simpler test. So that brings me to the second part of the talk, where I discuss these new constraint tests. So I first want to start with a quick review of how the plain Ligero constraint tests work. So we start with the encoded Ligero matrix. So this was previously on the right hand of the side. This is after the Reed-Solomon encoding scheme has happened. So first, the prover is going to commit to each column of this matrix. Or you can think of V as having an oracle to the columns. The verifier will provide a challenge consisting of the coefficients of a linear combination. The prover will take that linear combination, including one blinding row, and send the blinded linear combination of rows back to the verifier. So, right, one coefficient per row creates a linear combination of rows, and the prover then sends this blinded linear combination back to the verifier. Then, the verifier requests a set of T randomly chosen columns, which the prover had been required to commit to earlier. And so the main method for checking consistency is checking that the linear combination of the appropriate columns matches the appropriate coefficients in the linear combination that it had been sent before. And this is how we check the soundness and check whether the prover has cheated. All of this takes 4 rounds, not including the commitment at the beginning. The verifier sends the linear combination coefficients, the prover sends the linear combination of the rows, the verifier chooses the subset of the columns that we're committed to, and the prover sends them over. All of these things are done after the entire Ligero matrix has been determined and encoded. So all of this is happening on the encoded version. But in BooLigero, we add an additional step. The verifier will provide some challenge coefficients that will affect the unencoded Ligero matrix. So the verifier is changing the unencoded Ligero matrix before it gets encoded, then the prover encodes it, and then the prover and verifier finish the rest of the protocol as normal, using the same kind of consistency check as before. So another way of saying this is that our additional tests call the Ligero tests sort of as subroutines. Alright, I'm going to explain in more detail a test that will check that some number of variables have 0 for higher order bits. So this is a simple range test, right? Checking that X and Y both have zeros above a certain bit index. And I'm only doing 2 here, but this could be many variables. This can be essentially an arbitrarily high number of variables. So in this case, we have 2 variables that we want to test the higher order bits are 0. The prover is going to add an additional variable. This variable is chosen uniformly at random, conditioned on the property being true. So in this case, we pick a random variable A that also has its higher order bits be 0. The soundness here will hold even if this variable wasn't random. The randomness here is only used to blind the test, which will keep the verifier from learning anything about X and Y other than the fact that the property is true, which is already true if the prover wasn't cheating. This idea of adding this randomized variable is inspired by the circuit sampling idea of Baum and Knof from 2019. The verifier then sends binary challenges, so it sends 1 bit per variable. In this case, we have 2 variables, X and Y, so the verifier sends 2 bits, C1 and C2. And now, the prover is going to add an entirely new row to the unencoded Ligero matrix, which with the intention of revealing this entire row to the verifier unencoded. So it adds this variable v, and it'll use an XOR constraint, which is just a normal Ligero test, to enforce its relationship to x and y. Essentially, each variable has a 50% chance, determined by the challenge coefficient c, to be included in v or not. So the main idea here is that this variable is going to be revealed directly to the verifier, and both the prover and the verifier will still encode this row into the encoded Ligero matrix. So we can still do consistency checks between this row and all the rest of the rows, and the rest of the Ligero proof continues as normal. So we reveal this extra variable to the verifier because it will let us check an additional property. So if you notice that if x, y, and a all start with 0, then v will start with 0 as well. And if x, y, or a, if any of them, does not start with 0, there's exactly a 50% chance, based on the random challenge of the verifier, the c's, that v will not start with a 0. And if this happens, the verifier knows that the prover cheated and will reject. And that's true even if there are, 10 variables going into this v rather than just 2. So all that remains is to repeat this several times until we have the desired soundness, with independent challenges from the verifier each time. Note that in this example, right, I only used x and y, but we could have had an arbitrary number of variables, and the number of revealed variables would still be constant. So even if I have a million variables that I'm testing in this way, I still only need to reveal 40 variables in order to get to 2 to the minus 40 soundness error. So how does this affect the proof size? Well, it's almost the same as the previous proof size. It's the same asymptotically. The only thing that changed is that the prover is now sending this full unencoded row, in addition to everything else in the proof. And remember that this unencoded row is at most as large as the encoded rows of the encoded matrix, which we're already sending some of. So the overall complexity remains unchanged. It's still O of root c. It actually initially looks like this method should be larger than plain Ligero, but generally this process decreases the size for 2 reasons. The first reason is what I said before. We've packed the bits. So we had a constant extra overhead, right? We have soundness, many additional variables to reveal. And this constant extra overhead is worth the multiplicative decrease in proof size for working in GF2 to the W. The second reason that this might actually lead to a decrease in size is that because we can test many properties in this way, which I'll describe shortly, adding this row might allow us to significantly reduce the circuit size, because it may be much more simple to check a constraint in this way rather than to write a subcircuit using XORs and ANDs and check it as part of the main circuit with the existing Ligero constraints. So we may be able to shrink this matrix further. And the degree to which you'll be able to do this depends on your particular circuit and whether or not you can rewrite a significant portion of it with the tests that we have. So what tests do we have? We can constrain particular bits, not just entire words, and not just most significant bits like I was showing, but any arbitrary subset of bits in a word. We can constrain these to be 0. We can show that one wire is a masked version of another wire, again in a batched way. We can do parity. We can do rearrangements of bits within or across words. And power of 2 range tests are just a special case of constraining particular bits to be 0. And all of these tests can be batched in a very, very cheap way, in the same way that I described earlier, where there is only a constant number of extra variables depending on the soundness, and not at all depending on the number of variables to be tested. We can then use those simpler tests to as subroutines to create more complicated tests. The most important one is bitwise AND over words. That, along with XOR, allows us to compute Boolean circuits. We can also re-implement arithmetic addition and we can do range tests for non-powers of 2. And these are less well batchable, but they're still an improvement over re-implementing the same thing in Ligero generally. The AND test especially is very involved. I'm not going to go into it in this talk, but you can check it out in our paper. So how does this do for some standard hash functions? So this is a graph of proof size. Smaller is better. The light dots here are BooLigero. The dark gray dots are plain Ligero. And note that this is a log-log scale. So on something like SHA-2, BooLigero starts out with a disadvantage because arithmetic addition is actually an operation in the SHA-2 hash function. So Ligero can implement that natively. BooLigero has to essentially build an adder and re-implement that. Still, even with that, we do get a modest improvement. So for one iteration of SHA-2, it's about a 1.1x decrease. For many iterations of SHA-2, I believe 2 to the 15, it's about a 1.6x improvement in proof size. For SHA-3, we do much better because SHA-3 is sort of inherently a Boolean circuit, and so we can take advantage of a lot of the things we tailored for Boolean circuits. So here, one iteration gets about a 2.4x improvement. Many iterations gets a 2.8x improvement. These improvements are growing slightly because the overhead of the revealed rows shrinks relative to the rest of the proof size as the circuit gets larger. So there you have it. BooLigero improves upon Ligero in 2 ways. It packs W bits into each field element instead of just one, and then it uses a number of additional constraint tests that take in additional verifier challenges and incorporate that into a revealed row of the unencoded Ligero matrix. And between these, we get a concrete reduction in proof size. So you can check out more in our paper on ePrint, which I've put a link to on the screen. Thank you very much.